All right, 5.2 properties of rational exponents and radicals. That's a lot of words. Properties of rational exponents and radicals. So remember, rational exponents are like these, fraction exponents, and radicals are these things, weird roots. Okay, so we got rational exponents, we got radicals. So all I'm going to do today is give you a bunch of different rules that are involved with these things. And they're rules that we're going to try to practice so that they become second nature. All right, before I give you all these rules, I'd have to give you a little bit of recap from some rules that you supposedly learned in Algebra 1. Supposedly. But I taught many of you Algebra 1. And I taught some of you Algebra 1 during COVID, which I know you didn't watch the video. I know that you didn't watch it. All right, so these are exponent properties. We should have learned these in Algebra 1, exponent rules, okay? If these seem really, really foreign, they're pretty intuitive, so I think we'll be able to pick them up rather quickly. But just to jog your memory a little bit, if you don't have to write all this down if you don't want to. Remember, it's going to get posted on Google Classroom. I know that's a lot of writing. Here's what it is. I know this doesn't make any sense at all. Here's what it is. If you are multiplying things and they have the same base, so let's say I have like x squared times x to the third. Do you know what you do with those numbers? You add them, so it becomes x to the fifth. So that's one of our exponent rules. Or if you're dividing them, say you have x to the seventh divided by x to the fourth, I don't know. You subtract those numbers. That is a 7. It's a bad 7, but it's a 7. So when you're adding, or sorry, when you multiply them, you add. When you divide them, you subtract. Okay. These rules we'll really talk about today. The other two major rules, or three major rules I want to remind you of, is this one. If you have a power to a power, so like you have x to the third power. If you have a power getting raised to another power, what do you do with those numbers? You multiply them. So this would turn into x to the 9th. This rule is pretty straightforward. Anything raised to the 0 power is always 1. Doesn't matter what the number is. It could be 0 raised to the 0 power. It could be 342 raised to the 0 power. It doesn't matter. Anything raised to the 0 power is 1. And we talked about this a little bit yesterday as well. If you have a negative exponent, that means you got to flip. Okay? Yeah. I know you were trying to take a picture of me, right? Okay. All right. If you have a negative exponent, it just means you need to flip it. That's that rule. Negative exponents flip. All right, so that's a recap of Algebra 1 exponent rules. What? I'll reiterate again that the notes will get posted. Nobody checks Google Classroom, huh? Oh, yeah, remind me. Notes are going to get posted. Videos get posted. Cool. All right, so let me give you some new rules. All right? Going to be the main rules that we talk about with this whole idea. They are these two rules. And I bet just by looking at that, you probably know exactly what that means, right? You know exactly what we're talking about. Well, let me try to break it down. It says the nth root of a times the nth root of b equals the nth root of a times b. Naturally. And vice versa with division. Guys, here's all it is, all right? If you're looking at this thinking, what is that? Here's all it is. It means that if you have a bunch of stuff with the same, what was this thing called again? Index. If you have a bunch of stuff with the same radical and the same index, the rule is this. You can put them together or you can pull them apart. That's pretty much it, okay? So if they have the same index, you can put them together. Or you can go the other way. You can pull them apart and write them all underneath their own root. And it's the same thing with division. If they're being divided, but they have the same index, you can put that stuff together and write it all underneath the same radical. So that's pretty much the big idea. If stuff has the same radical, you can smash it together or split them all up. Okay? And we're just going to use that a ton over the next couple of days. So let's do an example of it. There's multiply or divide, simplify if possible. Well, let's just think about this. The cube root of -5 times the cube root of 25. Well, I don't know what the cube root of -5 is. I also don't know what the cube root of 25 is. So I definitely don't know what they are multiplied together. But there's a way we might be able to get around this. Are these the same index? Yes. It's the same radical. Since they are the same radical, the rule tells me that I can smash them together. All right? So I'm going to put them together. The cube root of -5 times, oh my gosh, -5 times 25. Since I'm multiplying, I'm going to multiply them underneath the root. All right, well, what is -5 times 25? Cube root of -125. Well, that's a little bit easier because 125 has a cube root, right? What's the cube root of 125? It's 5. And it's got to be -5 because it's -125. So this is just -5. Yay. So by using this rule where we can put stuff together, I was able to take something that is really ugly and figure out what it is, right? And that's kind of the gist of what we're trying to do. I'll do one with division, and then I'll have you guys try the other ones. Let's do this one. Square root of 243 divided by square root of 27. Are those the same roots? Yeah, they're both a square root. You can't do this if this was a cube root. If this was a cube root, you can't put them together because they're not the same. Okay? But since they are both square roots, I can put them together. I'll smash it. They're getting divided, so it's going to be the square root of 243 divided by 27. And now I can try to see what that is. 243 divided by 27, it's 9. So square root of 9. Well, that's easy. What's the square root of 9? 3. So you don't need a plus or minus here because we're not solving. It's a good idea, but since it's not like equals something, you don't need to add plus minus. Okay? Does this make a little bit of sense? All right, try these two on your own. Right, set, go. All right. Okay, so back in the first half of this class, we did stuff like this, where you were told to simplify this. Square root of 72. Do you remember how we did these? You broke it up, right? You broke it up using what? What kind of numbers did you need to use? All right, track. You needed perfect squares, right? You needed numbers that had a square root. That was because this is a square root, all right? So I know they used to be up here. They're not up here anymore. Can you think of any perfect squares that go into 72? So the perfect squares are like 4, 9, 16, 25, 36, 49. It's 36 if you didn't get my hint. Maybe multiple go into it, but 36 is the biggest, right? How does 36 go into 72? 36 times 2, right? So I could turn this into 36 times 2. Yeah. Like, are you asking, does it matter what this number is? No, it doesn't. All that matters is that this is a perfect square. Yeah, you just need one perfect square. Okay. All right, and then back in first quarter, we were using these rules that we were talking about today. You just didn't know it yet, because what did we do at this point? You'd split them up, right? You'd break them apart. That's what we're talking about today. This is all underneath the square root, so you can split it up into 2 square roots. Because it's the same root, you can break them up. And what is the square root of 36? So it's 6 root 2. So that's what we were doing last quarter. Now it's going to be a little bit different, because we're going to work with things that aren't square roots. Now it's a cube root, okay? So don't think too hard. What numbers do you think you need to use to break this up? Well, you're saying 8. Why would you use 8? Because 8 is a perfect cube. So here we were using perfect squares. Now you need to use perfect cube numbers, or numbers that have a cube root. So numbers that have a cube root. What are some numbers that have a cube root? 8, 27. What's 4 cubed? 64, I think. 64. Okay, you're probably not really going to get much bigger than that. All right, so those are cube roots. Those are cube roots. So we already talked about it. 8 goes into 80. 27 does not. 64 does not. But 8 does. So I can rewrite it as the cube root of 8 times 10. And then I can split those up, because it's under the same root. Cube root of 8 times cube root of 10. Well, what's the cube root of 8? 2. So this is 2 times the cube root of 10. Same process, just different numbers. So all you have to do is ask yourself, what type of root am I dealing with? Is it a square root? Is it a cube root? Is it a fourth root? And then, based on that, you got to use numbers that correspond with that radical. So you're using perfect squares here. You're using perfect cubes here. So what are you going to use here? Perfect cubes. I'll give you, maybe you'll use 125 sometime. I don't know. Perhaps. Maybe not. So why don't you give those 2 a try? You're trying to find those types of numbers. All right, here we go. This is now something that we have yet to do, okay? We had been breaking down radicals with numbers in them, but we have not broken down. We've not broken down radicals with variables in them yet. All right, so this is where we're going to end it today. We'll see if we can get through this. So it says to simplify, the square root of x to the 8th. There are a couple ways to think about it. There's like a technical math way, and then there's a little bit of a shortcut way. I'm going to show you both. I'll show you the technical math way first. Square root of x to the 8th, I don't know what that is. But I can write this as an exponent, right? You can turn it into a fractional exponent. What is it? Oh, like, yeah, I see what you're saying. It would be x to the 8th to the 1/2, right? because the square root is a 1/2 power. And then again, you have a power raised to a power. What do you do with those numbers? Multiply. So that is x to the 8/2, which is x to the 4th. Right? All right, so that's the technical math way to do it. You can also do that over here. I know this one's a little bit different. It's a cube root. We can think of m to the 15th raised to the 1/3. Power to a power means multiply, right? So that's m to the 15/3, which is m to the 5th power. You guys tracking with this? Okay, well, what if, I think this is the next one. What if we did one like this? Cube root of y to the 11. Well, that's y to the 11 to the 1/3, which is y to the 11/3 power, but it's kind of nasty, right? The problem is that it doesn't divide evenly, right? So when you're in a situation that it does not divide evenly, there is kind of a little trick that we can pull, all right? And here's how the trick goes. You ask yourself a series of questions. First, you're going to ask yourself, how many times does 3 go into 11? Twice. 3 times 3, or 3 times 2 is 6. 3 times 3 is 9. But 3 times 4 is 12, so then you bust, right? You're too big. So how many times does it go in? 3. So 3 times 3 is 9, right? So you're not bigger. So it goes in 3 times. So here's what you're going to write. You're going to write y, oh boy. You're going to write y cubed, because it went in 3 times. And then what's your remainder? So it goes in 3 times. 3 times 3 is 9. You have a remainder of 2, right? See what I'm saying? There's a remainder to get to 11. Here's what you're going to do with your remainder. You're going to put that underneath the radical, so it's a remainder of 2, right? So y squared underneath that. Okay? That might be, and then this is where you leave it. Yeah, I'll do it again. Don't worry. Let's do it with this one. Again, the first question was, how many times does 4 go into 13? 4 times 3 is 12. 4 times 4 is 16, so you're too big. So it goes in 3 times. So you have x to the 3rd, because that's how many times it goes in. And then what was the remainder? Bless you. 1, because you're trying to get to 13, right? 4 times 3 is 12. You need 1 more. So you put your remainder underneath the radical. So it's a remainder of 1, right? So it's just x to the 1st power, which is just x. You don't need to write the 1st power. You can just leave it as x. And that's it. You can use that shortcut at any time, and it will work. You can even do it here. How many times does 3 go into 15? Holy crap, m to the 5th. Whoa, how many times does 2 go into 8? Oh my gosh, x to the 4th. Shortcut works every time. Okay, so I showed you the technical math way first, but you can always do the shortcut. And when it doesn't divide evenly, you have to do the shortcut because there's nothing else to do, right? Does it make a little bit of sense?